It's a pleasure to be in Finland. It's 40 years ago that I was here first as a student. I was at the University of Hamburg, and I've enjoyed coming back many times since then. What I will do today is speak about work we're doing in Canada on carbon modeling and analyses of forest sector climate change mitigation options. And we have the same debates that are going on here in Finland, in Sweden, and Germany, and the United States, and everywhere. And everybody recognizes that forests can play a role in mitigating climate change, but how we best go about doing that is hotly debated. And so what I will be doing is giving you a little bit of an overview of the key issues that we're facing in Canada and some of the modeling approaches that we use for the analyses, and also talk a little bit about some unpublished work that is sort of in progress right now. So let me start by stating the obvious, and that is with just 1 degree of warming, the impacts of climate change are already being felt around the world. Whether that is forest fires or insect attacks, storms, permafrost thawing, peatland fires in Greenland, or melting ice caps. These impacts are occurring everywhere, and one of the things that they have in common is that many of them release greenhouse gases and change the energy balance through albedo, etc. So not only is climate change affecting forests and the land sector, but the land sector in turn is affecting climate change. And part of the reason that we have this problem is that the global average temperature increase, of course, is around 1 degree. But the expression of this is regionally differentiated, and we see in British Columbia and across Canada temperature increases in the summer annually that are in the order of 2 to 3 degrees, and winter temperature increases over the last 50 years that are in the 5-degree range. And I've seen similar statistics for Norway and other regions. So first important message, and this goes back all the way to Svante Arrhenius, that the increases in temperature will be higher in northern regions than the global averages. So we all understand, I assume, the IPCC report on 1.5 degrees that was published last fall. And the IPCC was asked by the international community, what would it take to keep global warming below 1.5 degrees? How can we get there? What kind of activities would be required? And what the report concluded was that we basically need to make dramatic changes in all sectors of our economy, whether that's energy systems, land, industry, buildings, transport, cities, everything must change dramatically, because in order to stay below 1.5 degree global average temperature increases, the allotted amount of carbon dioxide that we can add to the atmosphere is about 420 million tons of CO2. And of course, at current annual emissions of about 42 billion tons of CO2, that gives us about 10 plus years to address this problem. And coming back to the first point I made, there are a number of additional carbon releases from permafrost thawing, methane releases from wetlands, but also forest fires, et cetera, that could add another 100 billion tons of CO2 over the course of the century. And so there are basically not only the anthropogenic direct emissions, but also the sort of indirect emissions that come as a consequence of climate change that will affect the atmosphere. And what the IPCC report laid out was a series of choices that we need to make. And it highlights the dual role of reductions in fossil fuel emissions and increases in land sinks in order to achieve the desired greenhouse gas emission reductions in the atmosphere. And what this shows here are 4 scenarios from left to right, showing sort of the one with the most aggressive fossil fuel reduction strategy that would involve a smaller demand for the land sector to contribute net negative emissions. And then going to the right, a progressively less aggressive reduction in fossil fuel emissions, still ambitious relative to what's happening right now. But basically, the less we succeed in fossil fuel emission reduction, the greater the need for a strong land sink. And the numbers at the bottom show you the area global demand of energy plantations combined with carbon capture and storage that would allow us to achieve these goals. And you can see that on the right-hand side, 724 million hectares of land would be required, and that's roughly twice the area of India. So obviously, huge implications for global food supply, food security, competition for land, risks for further degradation and desertification, but also opportunities. If societies decide that climate change is an issue that we need to address, there are opportunities to do land restoration and rehabilitation and afforestation to achieve co-benefits as well as climate change mitigation. So in order to better understand what Canada's contributions are, we have developed a national forest carbon monitoring, accounting, and reporting system that focuses, as required by the United Nations Framework Convention on Climate Change, on the greenhouse gas balance of the managed forest. And so the map on the left shows in the southern forests, the darker forests are a managed forest, managed for the purpose of greenhouse gas inventory reporting. This doesn't all mean it's land that is used for timber harvest. This also includes many parks, riparian zones, and lands that are managed for purposes other than timber production. And then to the north of that, we have the unmanaged forest, where there's virtually no direct human impact. If there are deforestation events occurring, they need to be tracked and recorded. And then on the right, you see the map in which we currently represent the land management by splitting the country in some 600 management units, and representing the forest within that as about 3 million stands. And we then simulate the dynamics of these using the carbon budget model of the Canadian forest sector. I don't have time to go into all of the details of how that is done, but what fundamentally the model does, it's a data integration tool. It takes inventory and growth and yield data to describe the forest and its initial characteristics. And then it uses the IPCC gain-loss method, where we grow the forest and then subtract losses due to disturbances, management activities, et cetera. We have land use change data, both deforestation and afforestation. Canada maintains an active deforestation monitoring system for the whole country. And then we have a series of climate and ecological modeling parameters that are combined with this information in an aspatial way. And we then generate graphs like this. This is the NIR 2016 graph. And what you see here is in the bar charts, the area affected by insects, fire, and harvest activities. The blue line, the line with the blue circles, is the net greenhouse gas balance from the atmospheric perspective. So a negative value is a sink. And then the line above is that plus the emissions from harvested wood products. And if we just look at the blue line, what you see is that Canada's forests have been a sink throughout this period. Once you add the harvested wood products, you see them being sinks and sources. But the more important characteristic is the huge interannual variability. And the reason for the huge interannual variability is largely the contribution of forest fires, the red bars. And if you compare, say, 1992, versus 1995, you see that there's almost 270 million ton difference, and that's about 40% of the greenhouse gas emissions from all other sectors. And so this huge interannual variability is a problem. The other thing that you see, I'll come back to in a moment why it's a problem. The other thing that you see is that up to about 2000, we were always a sink, even after including the emissions from harvested wood products, with the exception of 2 years with large fires. But then after 2000, the picture changes, and we've been a source in almost every year. And the reason is clearly shown here, and that is the area affected annually by insects, in particular the mountain pine beetle outbreak in British Columbia, to which I will come back in a moment. So when I say it's a problem, it's a problem because this very large interannual variability does not allow us to show very clearly the trends that are due to anthropogenic emissions, anthropogenic activities. And so starting in 2017, we developed a new reporting approach. So basically, in order to address this problem of the very large interannual variability, and in order to more clearly see how changes in anthropogenic activities and mitigation actions influence the greenhouse gas balance of the anthropogenic component, what Canada has started to do is develop a methodology that allows us to separate the total remaining forest land emissions into two components. One that we call the natural disturbance component and the other that we call the anthropogenic component. I won't go into all the details of how this is done, but effectively lands that are affected by stand replacing disturbances or insect disturbances that cause more than 20% mortality are transitioned into this natural disturbance component, and they remain there until, in the case of insects, the biomass loss has been replaced by regrowth. And in the case of fires, it's an age-dependent period, so about 70, 80 to 100 years until stands that were affected by stand-replacing wildfires leave the natural disturbance component and return into the anthropogenic component. And the reason for that is that we can then report the emissions associated with natural disturbances in the natural disturbance component, but we also report the removals, the regrowth, the uptake of CO2 in that component. So what you see now is the black line was what you saw before, without harvested wood products. And you see that the blue line gives us the anthropogenic component, so the forests managed by humans, including the impacts of harvesting, but giving us a sink. This is not showing the harvested wood products emission there in a separate graph that will come next. And what you see, I'll show the activity data in a moment. And then you see in contrast to that, the interannual variability, a large interannual variability associated with natural disturbances and the trend of increasing emissions associated with that. And so if we take the blue line now, that's the same blue line you saw before, and add the harvested wood products emissions, now what you see is that as harvest rates have been increasing, that's the bars here, our sink has been declining. Then we had the global economic collapse, the sink has been increasing, then harvesting starts to resume and the sink has been decreasing again. So now you see a much clearer link between human activities and sinks and sources in the anthropogenic component of the remaining forest land. And now we have a hope to be able to demonstrate how climate change mitigation actions will actually express themselves as trends in the greenhouse gas emissions and removals, because against the backdrop of the very large interannual variability, it wasn't possible to see any consequences of human actions. And so having the ability to quantify and describe this in these reported emissions and removals, free from the interannual variability of the natural disturbances, is necessary so that ultimately the policymakers can see that there is a consequence of these actions and that it's worthwhile continuing to invest funds into these activities. So I started out by talking about climate change impacts and mitigation options on forests. I think we may start out by the general statement that the impacts of environmental changes on forests will be both positive and negative. We all understand that warmer temperatures and longer growing seasons can enhance tree growth, as can higher CO2 concentrations. But we also know that prolonged drought, warmer temperatures can lead to higher mortality and disturbances. So one of the goals is to understand where, when, and how climate change impacts will occur, because in order to understand that, we can design more effective climate change mitigation and adaptation strategies for the forest sector. One of the things that the people that are doing climate niche modeling are telling us is that the impacts of climate change are going to result in shifts in vegetation zones. And this is some work that was published a few years ago for British Columbia. I'm just using it as an example. There are similar studies for Russia and for other parts of the world that show very clearly that vegetation zones will shift. They will shift northward into higher elevations. And that will have significant impacts on very large areas of forest that may be increasingly maladapted and stressed. And the reason for that is that trees are currently adapted to their climate niches, and as the climate niche shifts northward into higher elevation, depending on where you are within your envelope, you might benefit from that. So the trees that are at this end of the spectrum may grow better. So basically this niche, climate niche concept basically says that as the climate niche shifts northward or to higher elevation, if you're at the temperature limited end of this spectrum, there's a probability that your growth will be enhanced. If you're at the southern end, at the temperature rich end of the spectrum, stress, maladaptation, drought-induced mortality, et cetera, will occur. And what we see happening in British Columbia at the moment is precisely that. Over the last 10, 20 years now, almost 20 years, we have seen in the interior of British Columbia, where you saw the big shifts in the climate zones, trees being increasingly stressed, higher insect incidences. The mountain pine beetle outbreak is sort of centered in the core of British Columbia. So we have this sort of spiral of climate change impacts with initial maladaptation, warmer temperatures allowing insects to increase. There's about 17 million hectares of forest in which pine beetles, mountain pine beetles, killed trees. And the total volume loss for pines is in the order of about 800 million cubic meters of wood lost. But now we're going to the next phase of the spiral, which is we've seen in particular in 2017 and 18, extreme drought conditions. We had what are called Category 4 droughts. They didn't even exist as a concept before 2017 because that was a three category drought spectrum. We had such extreme drought conditions that then led to forest fires that we had very large areas burned. And here's the area burnt in 2017, 1.2 million hectares, which is about 50% more than the highest recorded value since 1920. And it is about 15 times higher than the average of the area burned since 1990. And then 2018 happened, and the situation got even worse. We had 1.35 million hectares burned. So between those 2 years, 2.5 million hectares out of about 55 million hectares of forests were burned, causing huge emissions and affecting our forest carbon balance. And so I'm going to show you some unpublished data. This is basically an effort to plot net biome productivity, cumulative net biome productivity for BC's forests. And from 1990 to about 2002, we saw a cumulative sink that built up. Then the mountain pine beetle outbreak started, and we started seeing a decline in the source. By 2007 or so, anything that had been gained since 1990 is lost in terms of carbon balance. By 2016, we're at about minus 600 or so million tons of CO2 losses to the atmosphere. And then we had the 2 bad fire years, and we're now approaching close to 1 billion tons of CO2 loss. I have these big uncertainty bands on there because these numbers are still under development and under review, and in part because we now have data on fire severity classes, and so at first we thought that, well, some of these fires were not so severe, so we shouldn't use average emission estimates. But we also are now learning more and more about some very extreme fires with very high emissions, and so this is all still work in progress. But all this to say, the expectation of forests continuing to operate as carbon sinks is very much dependent on the impacts of climate change. And I know you don't have a lot of forest fires in Finland, but they have started in Sweden. And it'll be interesting to see how, and they're certainly happening to the east of you in Russia at a very large scale. So it's really going to be interesting to see how boreal forests in general will fare with climate change impacts. And to put this in perspective, the emissions from the wildfires in British Columbia in each of these 2 years were about 2 to 3 times the emissions from all other sectors of the economy, in the order of about 150 to 180 million tons per year. And what is perhaps even of more concern is that the fire intensities that were reported are beyond what most firefighters had ever experienced. And if you look at these pictures carefully, what you see is that there's a complete consumption of the forest floor. For this tree, even the roots that were connecting the tree were pretty much all burnt off, at least on the surface. And so the big question is, how will these areas regenerate with a loss of organic matter and the impacts of forest fires and future droughts? So let me switch gears and speak briefly about mitigation strategies and how we evaluate some of these. This diagram that I'm going to show you next is based on some work that we did with Gert-Jan de Boers and others in the 4th assessment report of the IPCC Working Group 3. This was done in the early 2000s and published in 2007. And at the time, the Kyoto Protocol was front and center, and the emphasis of the Kyoto Protocol was to maximize carbon stocks in forests. Countries could get credits for increasing the carbon stock in their forest ecosystems. And what the IPCC said at the time is that this is too narrow a perspective. We should not just focus on how much carbon we store in the ecosystem, but we really need to look at it as a system and understand the relationship between forest ecosystems and the use of wood products and biofuels that are extracted from forests, and then also the interactions with these products and fossil fuels and other products like steel, cement, and concrete that are emissions intensive. The IPCC also pointed out that if we expand forests into non-forest land use areas, that will have implications for agriculture and the ability to feed humanity, often with the consequence of either displacement, so deforestation occurring somewhere else, or if the agricultural land area is declining, then intensification of land use, usually associated with heavy machinery and fertilizer inputs, causing increased emissions in the agricultural land sector. And so the point of the IPCC was that instead of looking at how we maximize carbon stocks, we need to look at how we manage the land sector to minimize the net emissions to the atmosphere across all of these elements. For those of us who are scientists and understand that climate is not only affected by greenhouse gases, there's really another dimension to all of this, and that is we need to also look at the non-CO2 greenhouse gas non-greenhouse gas forces of climate like albedo and VOCs and other factors. And so this systems diagram now is really the basis on which we can discuss the current tensions in society around how we manage our forests, where one argument is we need to maximize carbon stocks in forest ecosystems. We must harvest less. We must allow these forests to accumulate more carbon. But we, as a consequence, will have less biofuels and wood products available to us. And that means we have relatively more emissions from fossil fuels and process such as cement manufacturing. And the alternative is to look at a system where we manage our forests to maximize carbon uptake. So we're less concerned with the absolute size of the carbon stock of the forest ecosystems, but we're concerned about the rate at which they remove CO2 from the atmosphere, and in doing so contribute to the net negative emissions goals that were laid out by the IPCC and others who try to keep temperature increases to a limited amount. And so the way in which you maximize the carbon uptake by forests is by managing their H-class structures in such a way that you have younger forests with high uptake rates, but that means you have to harvest periodically. You remove carbon from the ecosystems that then can be taken up again, and you use that carbon in wood products and biofuels, and depending on your substitution efficiencies, you do that, and in doing so reduce fossil fuel and other product emissions. I think the reality is that it's not an either or. It's managing our landscapes to achieve a mix of these objectives and also achieve other objectives like biodiversity, et cetera. But one of the reasons why this debate, I think, needs scientific input is because there is a wide divergence of views about the role of older forests and old growth forests in the carbon balance. Just this week, I had a report published came across a report that came out of British Columbia where the authors claim that old growth forests are carbon sinks indefinitely. And this is really at the heart of the problem, because if old growth forests were indefinite carbon sinks, then there's no reason to manage these forests in order to achieve greater sinks for the landscape as a whole. And so on the left-hand side here, you see a graph from a paper that Anthony Taylor and others in Canada published a few years ago, where they basically identified this sort of hypothesis of how net ecosystem production is affected in the old growth stage. And what you see is basically an A the sort of hypothesis of carbon sinks indefinite, B, which could be a flat line or sort of an oscillating line, as sort of the near carbon neutral state in old growth where the accumulation of biomass is balanced by the losses from heterotrophic respiration. And then C is where you have a situation where your old growth stage is actually losing carbon for the ecosystem as a whole. And so they then looked at some Eastern Boreal forest chronosequences of data, measured total ecosystem carbon stocks, and estimated net ecosystem production. And in this particular study, they found that these forests, even after about 100 years, started losing carbon as a whole. Both from biomass and dead organic matter pools. And there are a number of other studies that have been published in the last few years that clearly demonstrate that we have, certainly in the boreal forest, a number of old growth conditions where carbon sinks are minimal or even negative. In other words, their sources. This is, in my mind, this is a really important area that we need better data. Most of our permanent sample plots are not paying a lot of attention to these old forests. So coming back to the systems perspective, what that says is that when we want to design climate change mitigation portfolios, we need to account for three things: changes in forest ecosystems, changes in harvested wood products, and changes in the emissions from substitution benefits. And we always need to compare that to a base case. So here's the business as usual. Here's our mitigation proposal. How does it affect the carbon balance? Is it in fact climate effective? And so we've been taking the systems that we use to do our estimation and reporting for greenhouse gas inventories, and we've looked at options that are available to us in each of these three areas: the forest management, the management of wood products, and the substitution benefits. As I said, we use the tools that we use for our greenhouse gas reporting. The nice thing with the gain-loss method is that you can use the activity data from 1990 to the present, and then you just extrapolate scenarios into the future, so you have a seamless transition between your reported values and your scenario analyses of the future. And by doing that, we can then come up with estimates of greenhouse gas emissions and removal changes as a consequence of different mitigation strategies. I should also say that there's a whole economic component and socioeconomic component on top of that. I won't be speaking about it, but there are additional publications that deal with costs, economic costs, and employment, et cetera. I'm just going to pick one of the older studies here, work that Caroline Smith was leading on my team, to look at a national scale mitigation analysis. And I'm not going into a lot of the details here, just a few of the scenarios. So there's two types of graphs that I'll be showing you. The first ones are the cumulative emission changes. So if the line is negative, we have reduced the emissions. If it's positive, we have increased the emissions. First, let's compare two scenarios: no change in the harvest, just in the way in which we use the wood. If we shunt more wood to bioenergy production, we get a small increase in overall emissions. If we shunt more of the wood, and in this case it was 4% of the wood that would have gone to pulp and paper, instead goes to panels. So your lifespan increases from 2.5 years to about 25 years. So you get a climate mitigation benefit. And then there are different other scenarios. I won't go into details right now, and a portfolio that basically combines a number of different mitigation actions across the country to give us a regionally differentiated sort of best possible outcome under these set of scenarios. That was about 1.25 billion carbon sink enhancement, CO2 sink enhancement by 2050. Another way to look at these graphs, and I find this more informative, is by looking at the components that contributed to this. So here's a scenario where we harvested slightly less. When you see the green bar, this is the increase in carbon stocks in the forest by 2050, or the reduction in emissions. This is the reduction in emissions from harvested wood products. This is the increase in emissions from fossil fuels from long-lived wood products. Products that would be substituted by long-lived wood products and fossil fuels. And so if you harvest less, you have less of that material that you can use for buildings or fuels, but you have a greater sink in the forest and you have less emissions from harvested wood products. If you harvest the same amount and use some of that wood for long-lived wood products, this is again that 4% of the wood that would have gone to pulp and paper is going to panels. And you see by 2050 you get a larger mitigation benefit. You reduce the emissions from harvested wood products, no change in the forest because you harvest the same amount. You get a reduction in emissions associated with the building sector and a small increase in emissions from fossil fuel use because you have less biomass available to substitute for fuels. And so then you can explore a whole bunch of other strategies. I won't go into the details, but the largest, so the first two I showed you were these two over here. There's a whole bunch of other scenarios, and then a regionally differentiated portfolio that gives us this overall mitigation benefit with the distribution in forests and the substitution benefits and increased harvested wood products emissions. So by being able to break it down like this, you can now engage with the public and the policymakers and say, okay, these are different strategies. They're achieved by either storing more carbon in forests or in harvested wood products or substitution benefits, and these have different consequences. Storing more carbon in forests means you expose your carbon to the risk of natural disturbances, which, as I showed you for British Columbia, is a really big issue right now, and as it is for other boreal regions. Achieving substitution benefits means you have a benefit to the atmosphere that is not reversible. Reducing harvested wood products emissions the same. But increasing them, of course, then you have the negative impact on the atmosphere. And the other thing you can now do is start looking at uncertainties. You can start look at assumptions related to leakage or consumer behavior, substitution efficiencies, et cetera, et cetera.
So this is the annual snapshot for 2050?
This is the cumulative. This is the cumulative by 2050. Yeah, I mean, this is 1,000 megatons, right? Over 1,000 megatons. So it would be nice if the forest sector can do 150% of the emissions. But going back to that same diagram and starting with a systems diagram, so what we have done effectively here with that portfolio is we have increased the sink and reduced emissions from the forests. We have increased the rate of harvest relative to the baseline. That provides us with more biofuels and wood products, and allows us to reduce emissions in the other sectors. So green, the blues, and the red. And what we have learned with all of this is that how we use the wood that we harvest is critically important. I had a number of people ask me yesterday and in the media the day before, should Finland be harvesting more? And well, first of all, it's really important that we understand how we use the wood. And secondly, it's important that we quantify the impacts on the forest. And so let me, sorry, I just realized this. I see something different than you do. So the two things that we need to understand are the carbon retention time and the displacement factor, because the longer we retain the carbon, the better out of the atmosphere through the wood product use, the better off we are. And the higher the displacement factor, so the more emissions reduction we achieve through the use of the products. And so the Holy Grail in this are basically the long-lived structural building materials that give us both long carbon retention and high displacement factor. And so yes, Finland could have a climate-effective mitigation strategy by harvesting more, but it's not how much you harvest, it's what you do with the wood that matters when it comes to achieving climate change mitigation. And so what we're doing now is we're moving to fully spatially explicit analyses because we want to do this to better calculate costs and also location of facilities, et cetera. I have to really speed this up. And we're moving to next generation tools that allow us to do this fully spatially explicit. And the reason we want to do that is because we now have Landsat time series that Mike Wilder and Joanne White and Nicholas Coops and others at UBC have been developing that allow us to get 30-meter resolution time series of the areas that were harvested or affected by forest fires. And it's this kind of information that we want to use to drive these models of carbon balances. And so here's basically another version of the map that you just saw a moment ago for a slightly shorter time period, showing you where the forest fires are. Note that much of these forest fires occur in what would be considered the unmanaged forest. And so now let's see if I can make this work. Nope, we have the same problem we had before. It's working on my screen, but it's not working on your screen. Anyway, let's skip it. Basically, what this shows, unless we get hung up completely again, what this is supposed to show you now is the animation of taking this remote sensing information about where fires and harvesting occur to then calculate the dynamics of the carbon stocks and carbon sinks. So the modular spatially explicit modeling framework that we're talking about also has new modules that we're able to develop now, such as for mosses, for peatlands, for environmentally sensitive growth and yield functions, etc. And I'm going to skip this. Let me just wrap this up with a couple of comments on research needs and then conclusions. Where I see the biggest questions right now around this whole topic of climate change mitigation is first and foremost the age dependence of forest carbon sinks. It's really important that we understand whether and how forest carbon sinks change with stand age, because it is going to be a central piece of information about how we manage landscapes. The second set of questions is around the climate change impacts on growth and mortality, but also on decomposition rates, permafrost losses, not a big issue in Finland, but certainly for the rest of the circumboreal region, very important. The question that will be addressed by the IBFRA research project is what are the opportunities to enhance carbon sinks, and while at the same time safeguarding other ecosystem services like biodiversity. We need to start to design mitigation and adaptation strategies where we consider climate change impacts and the risks of disturbances. A strategy that is focused on storing more carbon in the forest, as we have done in British Columbia with fire suppression for a century, is obviously one that is fraught with risk if you enter into the world of climate change. We also need to understand what we should be doing after we have had disturbances. Should we be salvage logging the dead trees? Should we what kind of post-disturbance rehabilitation should we do? We need to understand the impacts of non-greenhouse gas climate forcing, albedo, VOCs, etc. And then in this whole discussion around the bioeconomy, we really need to understand how through our wood use we can increase carbon retention and substitution benefits. I talked earlier about the importance of the building sector. And I think we need to really have discussions at the global scale about what are realistic biomass supply trajectories as many, many different sectors are looking at biomass to solve their fossil fuel emission problem. I think it's becoming very quickly clear that there's not nearly enough biomass in the world to substitute fossil fuels entirely. I'll skip the IBFRA one. You'll be talking about IBFRA in a moment. Let me conclude then. When we design climate change mitigation portfolios in the forest sector, we should account for changes in carbon in forest ecosystems and harvested wood products, and for the substitution benefits relative to a base case. Only if we look at the system as a whole can we come to conclusions that clearly quantify the impacts on the atmosphere. It's also clear that there's no single strategy that is best everywhere. In areas where you have high disturbance risks, you will want to choose a different strategy than in areas where you have low disturbance risks. If you have a relatively degraded landscape or primary forest landscape, you have different choices that you can make. When we design climate effective strategies, we need to include substitution and harvested wood product storage. And that leads to an important aspect, and that is those who manage the forests do not control how the wood is used. What we have right now is that consumers make choices. They've forced forest companies to certify and follow certain guidelines. I think as producers of wood, we should start working with our consumers and ensure that the wood is sold primarily to those who use it for long-term products and high substitution benefits. The forest sector provides unique opportunities and I believe has a responsibility to manage sinks and contribute to negative emissions. But there are also very large risks of sources due to the climate change impacts. As we design mitigation strategies, we need to anticipate climate change impacts, and we need also to consider how we can design mitigation such that we can also contribute to adaptation goals. And lastly, and perhaps most importantly, let me remind you that, of course, none of this makes any sense unless we also reduce fossil fuel emissions very quickly, Because if we fail to do that, the land sector can not only not solve the climate problem, it's at risk of becoming an even bigger source as the world warms due to high fossil fuel emissions. And with that, thank you very much. Publications are available here, and there's references at the end. I can share this later. Thank you.
Thank you, Werner, for excellent talk. How is our mic? So, floor is open for questions.
Hi, again.
Thanks again. About your point that the forest owners do not really control about the way the forest or where we use the forest. Like in Finland, I guess currently 60% of the products that we have are like pulp-based, short-lived products, and mainly driven by the Chinese firms and companies that are really into this paper stuff now. So how can you say, what is the strategy to kind of create the demand for the long-lived products in this world?
That's an excellent question, and two things. So I know that in British Columbia, for example, and in Canada, we have a number of initiatives that work with our export markets and the users of wood. Canada, for example, has training centers in Asia, in China, I believe also in Japan, to basically help local craftsmen learn how to do timber frame construction and massive timber construction, etc. And so basically creating the demand locally by helping them better understand the opportunities and the benefits is one way to do it. And just to put things in perspective, the world right now is building enough floor space that is equivalent to the floor space of New York City every 35 days. And the forecasts are that we will be doing this for the next 35 years. The forecasts to 2050 are saying that floor space of New York City will be built every 35 days. So there is a nearly infinite demand and opportunity for structural lumber, mass timber construction in mid-rise and high-rise buildings. And I think the forest sector, if we really want to make a climate change mitigation contribution, that is one area where we can move wood out of the forest, let the forest regrow and remove more carbon dioxide from the atmosphere. And instead of putting it into short-lived products, we put it into long-lived products, store it out of the atmosphere, substitute for steel and concrete, and basically contribute to climate change mitigation. And as we make round things square, to put it into building materials, we have side products that can be used for pulp and paper or for bioenergy, etc.
What are the incentives for that? Like do tax,
Well, so what is happening is that Vancouver is the first city in North America that now has a policy that all new buildings must have an assessment of the embodied energy associated and the embodied emissions associated with the construction. Various building processes already have energy efficiency standards for the operational part of the building, but not the construction. So Vancouver is the first city in North America that is starting to ask builders to quantify the emissions associated with the construction. Just like when you buy a refrigerator or car, you have a sign of energy efficiency. We can make similar standards for buildings, both for operational and for construction. And so that's one way in which we can create incentives and show people, look, you have a choice to make. You can build this building out of concrete and steel, and your impact on the environment is X, or you can build it out of wood, and your impact on the environment is Y. And hopefully Y is a lot smaller than X.
Then we have a next question.
Okay.
It's not going. It's going to the recording, not to.
So hi, Werner.
Hi. Good to see you
Tuomo
again.
Kallioksi from University of Helsinki. You had a nice talk again. I have 3 questions. Could you please tell me what processes are determining that your old forests are sources in British Columbia? You referred to the different studies. And then could you say something about displacement factors you used in your calculations? What was the range? And then the third one is a little bit wider. It seemed to me that in your calculation you had fixed inertia use, how much we use inertia. So do you really see that we could shift from fossil fuels to the biomass-based world and still have same energy use, amount of energy used, and still reach the climate objectives?
Yeah, so start with the last one. I mean, it's absolutely clear that we cannot replace all fossil fuels with biomass. And I never said that. To the contrary, I said exactly the opposite. I said we will not have anywhere near enough biomass. What we're showing in these analyses is the way in which a decision about switching from a fossil fuel source to a bioenergy source will influence your greenhouse gas balance, right? And so one of the things, coming back to the second question about the substitution benefits and so on, I don't have the numbers in my head right now. I think that 2014 study was still based a lot on the Sathra and O'Connor review, the 2011 meta-analysis, which in that particular case had, I think, a substitution factor for the building material of 2. So for every ton of carbon that you add to the building, you avoid 2 tons of emissions. The most recent study that came out of EFI has scaled that back to about 1.6. But there's also methodological differences in terms of the bioenergy fossil fuel substitution, and those values were much lower. I think they were around 0.5. And again, I can give you all the public, it's in the publication and there's subsequent publications too. But one other thing that these studies don't do, and in fact, none of the studies that I'm aware of are doing, is that when we make projections into the future, we typically assume that these displacement factors are constant. And of course, technology will evolve. The energy efficiency of the energy sector will evolve. The energy efficiency of the building sector will evolve. And so as our competition gets better, our displacement factors decline. And that's something we need to be aware of. For the old growth studies, I did say that this was a study from central Canada, not from British Columbia. And I also pointed out, or meant to point out, that there are clearly huge differences, right? These A, B, and C hypotheses, we can find examples of A, as Sebastian Luceriad did in his 2008 paper. We can find examples of B and C. There's a very nice study in Sweden going on right now with flux towers that also shows an example of C, where the old growth forest is a carbon source, as determined from flux towers.
The main processes in those cases where old forests are carbon sources?
It's basically an inability of the biomass to continue to accumulate carbon. So an old growth forest on the west coast of British Columbia, where trees can reach ages of 1,000 years, is obviously a carbon sink for much, much longer than an old growth forest in the foothills of Alberta or in eastern Canada, or even in central British Columbia, where you have different tree species and different processes at work. So, and this is really the challenge of all of this work, is that whenever you begin a discussion around that, you bring in ecosystem complexity, and the answer always has to be, it depends, right? But just as we cannot say that old growth forests will be sinks indefinitely, that just makes absolutely no sense, we cannot say that old growth forests are always carbon sources, right? And that's why we have this ABC, and I had it as the first research item. We need to much better quantify not only the biomass dynamics, but also the dynamics of dead organic matter and soil, because even if the biomass is declining, as we see often in yield curves and in measurements of permanent sample plots, the carbon doesn't go into the atmosphere because the tree dies. It can be accumulating in dead organic matter pools or even in deep organic soils and peats. And so the difference in these ecosystem responses to age and climate warming needs to be better quantified if we want to design mitigation strategies that take these things into consideration.
So was it only biomass
Sorry,
or also soil?
The study that I showed you was total ecosystem carbon. Yeah, that was total ecosystem carbon.
So thank you. I think that you have much more questions, and this that starts to be really interesting. But we have to store the questions to the coffee break and to the panel discussion, and continue with the program and next speaker. We thank you once again, Werner.
Thank you.
You will have a floor in panel discussion, and we will continue with the next talk, which is given by Mikko Peltoniemi from Luke. Okay, Mikko, floor is yours.
Thanks, Werner, for very interesting talk. And as Werner also. Okay, thanks. Okay, so as Werner also, I do have a quite broad title. So to complement what Werner said, I present like some recent modeling activities that we have done here at Luke, and also together with our collaborators to better understand the potential of forests to mitigate carbon. So, as you know, forest land of Finland is a net sink of carbon presently, but there are like big spatiotemporal variation in net fluxes from the forests. And mainly these are caused by harvests, and also soil type has a big impact. Particularly when we talk about managed peatland forest soils, which are a huge emission source in the Finnish inventory. So if we look at these managed peatland soils, so forest soils, approximately 14% of Finland emissions are from those. They offset upland forest carbon sinks quite a bit. So few mitigation actions have been conducted in forests of Finland and in these peatland soils. So there's a really tremendous potential. So to put everything under a very broad overall aim, so that is to quantify and spatially identify net sinks and sources of carbon in Finnish forests, and in future also to plan and prioritize mitigation activities. So the presentation is composed of 3 associated studies, which are still quite independent. One is related to the spatial identification of peatland emission hotspots in forests. That's a case study from northern Karelia. The second study, sub-study, is related to developing forest GIS data sources for facilitating net sink and source estimation. And also that's related to analyzing spatial distribution of biomass carbon changes. And finally, this is something what we do also with our collaborators at University of Helsinki and Syke. We are setting up simulations to complete spatially explicit carbon budget of a catchment in Finland. So if we take first a look at this Northern Karelia case study, so we had some real management unit data from Northern Karelia. So these are state forests, and the data includes something like 700,000 real forest management units, and 120,000 of those are peat soil forest polygons. So that information covers forest cover and biomass and basal area, ditch age, depth and spacing, and also information about fertility. The question was then, which of these polygons will emit most CO2 to the atmosphere? So we built the analysis based on the recently developed model here at Luke. Antti Jussi will tell more about that model. It's basically a simplified mechanistic model that simulates hydrology of peat soils. It takes some key parameters as inputs. That's the kind of like a biomass and cover of trees on the sides, and uses that information to calculate LAI. It also accounts for the drainage status of the site and soil quality, kind of like for the hydraulic properties. It produces predictions like per 1 day. And as you know, this peat soil groundwater table is very important for the emissions estimation because it kind of like determines the aerobic and anaerobic conditions in the soils. And in the aerobic conditions, like lots of CO2 is emitted. When the water table is high, more methane is emitted. So in this study, we linked this hydrological cycle and water table level to the CO2 equations produced by Paavo Ojanen earlier. Okay, so here are a couple of examples of these spatial simulations in 20 polygons in this Northern Karelia region. So we can see like clear differences in the water table depth in these example soils. And these are mostly covered, kind of like explained by the forest cover and transpiration from the site. Also, ditch spacing affects this water table variation. So clearly on some of the sites, water table never goes very deep, but on more forest covered sites, it goes deeper. So here is a prediction of like average soil CO2 emissions per 1 year. So this is kind of like a net emission from the soil only. So this does not cover the forest growing above the soil. So we can like clearly see variation in the emissions from these soils. And there are clearly a couple of like hotspots in this area which show like very high CO2 emissions. On those sites, the water table is low. There's a big forest growing on these areas. So there's like very good question what to do with this forest in the future. They might be like very suitable for continuous cover harvesting, for example, and those kind of like operations should occur there first rather than elsewhere. So, but all this was done with the material from state forests, and it doesn't cover the entire Finland. So the question, we basically want to replicate these kind of analyses for the entire Finland. So that sort of information are hard to get except from these multi-source inventory maps that NFI is producing. So basically these multi-source inventory maps cover combine field measurements, satellite images, and digital map data, and they are processed to form thematic maps of forests across Finland. The one problem with this thematic map is that they are massive. So running like dynamic models with this material becomes complicated. So we decided to go or reduce the amount of data a bit by segmenting these thematic maps to homogeneous simulation units. So the segmentation of the thematic maps was based on soil class, property borders, stand height, and species spatial areas. And based on these, the segments were formed. Rest of the thematic map materials, well, actually that's there also, but DPH, for example, was summarized to these segments as mean values. So these segments are shown in this figure, or kind of like you can see like these areas formed by small pixels, which are kind of like these original 16 megapixels of the thematic maps of NFI. They well identify peat soils, and they also obey property borders of forest land. They may not always like equal real forest management units, but that's a compromise we need to take to reduce the amount of data for calculations. The question is then how well they really describe the distribution of the real data in forests, and are they suitable for change analysis? For example, there might be like two of these like segmented maps, and comparing one to another, one might make kind of like analysis of the changes of biomass between the different time points. So if we look at these distributions, we see that first these NFI plots show the widest distribution. So on the x-axis, one has now biomass, and on the y-axis density. So NFI plots like show the wider distribution. Segments and pixel-based biomass maps, on the other hand, show quite similar distribution. So we don't do much mistake when doing this segmentation in comparison to these multi-source thematic maps. And if we calculate the biomass from these segmented maps for the entire Finland, we get quite close to the same results as from the original NFI plots. Okay, so here's a picture about the change analysis based on this thematic map made by Markus Haakana. So there was a thematic segment map made for 2009 and 2015, and Markus calculated the difference in biomasses in these maps, between these maps. And one can clearly see kind of like decreases of biomass in the subtraction graph on the right. So this map is from the Joensuu region now. So the segmented data from two separate periods seems suitable for detecting harvests. And this is some kind of like very useful map information for feeding dynamic models, for example, where to allocate harvests into retrospective analysis. So then I will just show one slide about combining these segmented maps to dynamic models that is predicting forest carbon balance and growth. So the model is called PREPAS, and we are doing this work with University of Helsinki, Annikki Mäkelä and Francesco Minunno. And also Syke is participating in this particular exercise where we are mapping the full carbon balance of Kokemäki-Joki region. So as a summary, I could say that the combination of a mechanistic hydrological model and empirical peat soil emission model clearly pinpoints emission hotspots on map, and that is very useful information for planning forest management for mitigation. The segmented forest maps seem to also provide useful information for further model analysis, and they definitely improve the simulation efficiency. As a result, we will in future get better identified sinks and sources in the Finnish forest landscapes and forest stands. So nationwide applications and scenarios are in plans, and that's what we are going to work in future. So that's it. Thank you.
Thank you, Mikko, for excellent talk. Now we have time for a few questions before coffee break. Anyone ready to ask?
I guess I have one. Mikko, when you do the dynamic modeling, how do you grow the trees? Do you have yield functions? Do you have process models? You were referring to Annikki Mäkelä.
Yeah.
I mean, she does process modeling. Is that what you use to drive tree growth for
Yes.
these? And is that environmentally sensitive tree growth then? Do you have climate variability, interannual variability in climate to influence your tree growth rates?
Yes, that actually is a dynamic model, a process-based model that Annikki and has been developing, and I have developed some carbon flux components for that model. And this carbon flux component accounts for daily variation of weather, and that is then translated to growth variation. So yes.
And daily time steps?
Daily time step, yes.
Okay, thank you, Mikko, for interesting presentation. I'm Boris Čupek from Luke, also working on soil carbon modeling. And I'm interested. You made a statement that it's quite successful to combine a mechanistic hydrological model with empirical peat soil model, and I think perhaps it's successful, but I think there is a lot of potential for developing of this model for sure.
I completely agree.
Yeah.
I mean, the data sets. I mean, there's like quite a big data sets, anyways, from which these empirical models of soil emissions were developed. But I mean, more data is still needed, and that also needs to be complemented with this tree carbon sink or vegetation carbon sink.
Yeah. So, do you think is there any potential that this model should be developed in the way to prevent emissions? For example, if in case of drought there could be fire, like a fire module. Have you been thinking about?
Yeah, we've been thinking about linking these different types of natural disturbances to this segment map and also to these PREPAS simulations. So yeah, that's something we hope to do in future, yes.
So thank you for coming back. We will continue this seminar with 2 more presentations, and then I will shortly introduce IBFRA work, and then we go to panel discussion. Without any further introduction, I will give floor to Antti Jussi Kieloa, who will give the next talk. Floor is yours, Antti.
Thank you. I will talk about our ecosystem modeling lab team and about the eco-hydrological modeling, what we are doing. As Raisa said, I'm in the list the first. We have 3 postdocs and Samuli Launiainen, who is kind of like the team PI. So he is the main person who has been writing these codes, and we are developing those further. Here's a short outline of my talk. So I'm first introducing you our main models, PyApes and SPAFU, and some ongoing applications, what we are using them for. Mikko already mentioned one of the applications of SPAFU, but there is one more what I'm introducing to you. And then some future plans of ecosystem modeling lab. So of course, because we are mainly postdocs, so what is the kind of where we are directing with these tools in the future? So the first, our main workhorse is a PyApes. The acronym comes from Python Atmosphere Plant Exchange Simulator. It's a soil vegetation atmosphere transfer model. It's a mechanistic one. So it means that it uses mainly physics to explain everything. So it is not statistical way of describing the ecosystem functioning. It gives out possibility to investigate responses of one forest stand for example, climate change, what changes in the stand structure have an influence, for example, soil, water, and heat balance, or for example, if we are doing some forestry practices, for instance. Or the species composition, for example, if we want to change the moss layer characteristics, which kind of influences it has to the energy balance above ground and also the below ground. So this is quite detailed. It's a one-dimensional column model. So it is divided into multiple layers, which can be multi-species, and it mainly describes at the moment water, carbon dioxide, and energy flows. And in case of carbon dioxide, it is mainly the living part. So in the soil, at the moment, there is no decomposition model inside there, but I kind of like come briefly in that in my future plans. What is the ongoing applications of this PyApes model? For example, we are using it for really intensively studied Hyötyälä forest fluxnet site, and we are breaking kind of the measurements. We are using the model to interpret the measurements so that we can see why the carbon sink increases in this specific site and which kind of interactions there are going on. For example, what is the amount of carbon dioxide or leaf area index is increasing, what is the kind of like driving forces of this increase. Another one is what drives the hydrological responses to harvesting. So in the Lettosuo, which is drained peatland site, there is 3 different treatments: clear cut, control, and then this partial harvest where is continuous cover forestry. So we are looking which kind of effects these have for the hydrology in these forest stands, and why we are doing this is because the clear cut needs the ditch maintenance and the partial harvest doesn't. So if this works out, then we have more information about how the hydrological responses of these forestry treatments have. Then there is one ongoing Academy of Finland project of Samuli Launiainen, and it's because this PyApes, it's kind of like what is most specific thing about it is that it has surface covers in it as a separate module, and as a Boreal region, the moss is really important of these surface covers. So we are developing further this moss layer description, and in the same time pinpointing the most important functional traits which the mosses have. And by what it means that we are describing more efficiently the energy-water balance description of this, also including this Varkuhar type photosynthesis, respiration, and growth and of course mortality. So what is the input of the decomposing parts to the soil, organic carbon pools. And of course, there is plenty of other surface covers, what is included in PyApes models, like bare soil, litter, snow. Of course, we are at the north. Then we have another one, what was already mentioned by Mikko, this buffer model. It comes from the words spatial forest hydrology, and it's semi-distributed catchment model. What means semi-distributed is there is a top model approach which is distributing the water inside the landscape. It's a simple spatial model, and as in the figure, it's kind of like simplified version of the PyApes, and it only at the moment describes the hydrological part of the PyApes. The soil is not, there is 2 levels or 2 buckets which are accounting the water status in the soil. So there is also moss layer and the soil in this model 1 grid cell. It runs with the daily forcing data, and it uses the open GIS data like soil mappings, digital elevation models, but also it draws everything from the national inventory data for the canopy part, for instance. And it is made for the need for the practical forestry applications. And here is the one example of it, forest trafficability. So when there is a forest like clear cuttings or harvesting done, heavy machinery is going there, and it may even sink into the soil and get stuck there. So this is the kind of like way to make forecast when it's really good time to go there, because due to climate change, we don't have any more soil frost to carry this heavy machinery. And Jari Perttunen has done nice demonstration, and it can be found from that website. It runs for the real time and showing the one catchment area in Vihti, where it can, in this kind of like soil moisture and trafficability things are in there. Okay, then the future plans of our team, postdocs. First, Kersti, she's going more into details of this PIAPES model, and because it's coming from the leaf scale to the whole forest system, it gives a good opportunity to link the isotopic signals of carbon and oxygen actually to this model. There is increasing amount of experimental data already, but it hasn't been included in the models yet that nicely. And the problem is also that there is a scaling difference in the spatial from the leaf to the whole ecosystem level, but also the time scale difference from the leaf scale, like milliseconds, to the whole forest thing. So these are the problems what Kersti is going to tackle in this modeling study. What I'm going to do, I'm going to dig more deeply into the SPAFHUS life and doing the spatial heterogeneity. I'm going to add the carbon model into the soil, and it means that it will be also included in the PIAPES as well, because it's really good way to test it as well. And there will be a radiation scheme as well. So we can get the microclimate there, and we are changing the hydrology description so that it's a distributed model then. So the grids are interacting with each other, which is not happening at the moment. And this gives us the possibility to study biogeochemical reactors, pipes, and reservoirs, and the interactions between them. So if we are doing the forestry practices in some part of the landscape, we can see that does it have an effect in some other neighboring biogeochemical reactor pipe or reservoir. And also there is a spatial aggregation, so now we have tool to kind of to see that what happens when you are scaling the stand scale to the global scale, for instance, because normally there is no landscape or regional level model in between. So this kind of like gives us a kind of like tool how to tackle these aggregation problems in the biogeochemistry. Then finally, the Pavel's. Pavel is not going directly to the working with models, but he's doing a good job to provide us spatial data, and especially so in thermal imaging. In his plans, there is three different categories. One is the analysis of the near-ground air temperature fields, and especially detecting there with a thermal camera the organized structures. So this is the kind of like basic micrometeorological work what he's doing. But there is also the most thermal properties. So we want to get the surface cover right. So we need to information, for example, emissivity, the responses to drying, canopy temperature is something really important because it is species-specific trait what has to be studied more further. And the last in the there is the UAV, means drones, the thermal survey of boreal ecosystems from the drones with thermal imaging, and it gives water stress index, soil moisture, but also from the canopy, the stomatal conductance, and sensible heat fluxes. So this was our ecosystem modeling lab theme. Thanks for listening. Any questions?
Thank you, Antti Jussi, for nice introduction to teamwork, what you're doing. I will bring the mic.
Thank you very much. That was very interesting. I'm Maria Holmberg from the Finnish Environment Institute. I have two questions. First, about you mentioned this that you're studying trafficability with respect of the wetness of the soil. But are you looking also at frost trafficability from the point of view of whether soil is frozen or not and how well it's frozen?
We are doing, I'm not that involved with that part, we are doing, I think, it is taking into account the frost as well, but also the roots and stuff like that. So it's a kind of, it takes a lot of the Aura Salmivaara, whose name was there in the list, is especially the person who is doing the kind of integration of these, our model simulations with the other risk assessment parts. And I think that he has been mentioning that there is plenty of other than just wetness.
Thank you. And then the other question was about the lateral fluxes. You had this mention that you will look in the future. You have this more distributed hydrological model there. And so I'm thinking about, do you also look then at the carbon transport of elements? And if you, because there are groups in our institute who are working on that, so it would be nice to have some discussions in more detail on that.
Yeah, in some extent, yes. And this would be actually nice to know what is going on in the city. So please give me some names and we can have a nice discussions.
Thank you. Do we have any other questions from the audience? If not burning questions, we thank again Antti Jussi for a nice presentation and continue the program with Jari. If you change the mic, and I will change the slides. Okay, floor is yours, Jari.
Okay, thank you very much. Thank you for invitation to come here. I'm going to present some work that we have done together with Professor Tuula Packalen in the context of recently finished Horizon 2020 project Diabolo. Actually, I like to think this approach as a more in a bigger picture. So I call this, I have invented it personally, this term EFDM approach to study land use climate impacts on forest resources. It sounds like it's a big thing. And it's currently a 3-paper series. We expect some extensions to this series later, hopefully this year. But as you can see, we have studied climate and land use issues from different perspectives, and we have published them as peer-reviewed publications, so you can find details about those. Then what is this EFDM acronym that is given in the title? It stands for the European Forestry Dynamics Model, which is a matrix model for simulating the development of forest under specific management. It's something that you can download as open source code, and it has been prepared as an assignment from the Joint Research Centre of the EU. So you can find it from EU Science Hub or however it's called. So basically what I want to present today is half of this model, because I think it's a very clever modeling system that certainly deserves more attention than it currently has. And then as a case study, how we can approximate uncertainties related to climate change and forest management. So I don't want to say the final word. I don't want to quantify what kind of uncertainties we have related to these topics, but I present an approach how we can account for this kind of aspects. Some key principles of the EFDM model. The initial state of forest is presented in our model as this kind of matrices. So we can classify our forests, for example, using age and volume as classifiers. And as the initial state for our model, we need the area which is in these matrix cells that are splitted, for example, in terms of age and volume. Well, in practice, we need these matrices for all elements that determine forestry dynamics. So we need to have more than one matrix for different site types and species and so on. So this is the state of the forest, and in addition we described something that is called transition probabilities for forest areas in the same kind of framework. So these transition probabilities give the proportion of area that is estimated to move in the matrix. Because of natural processes, the movement, the forests grow in volume, they gain age, so they move in that direction, for example. Because of treatments, if we do final felling, a clear cut, then the forest area is returned back to the beginning of the rotation. If we do thinning, there is another kind of effect, and so on. So we need to characterize the forestry dynamics for these matrices. Then the simulation steps are obtained by multiplying the different matrices together. And this diagram is read from the right-hand side. So there is our initial state, and for technical reasons it's presented as a vector instead of matrix. So it's rearranged for the computation. Then there are JA matrices, two of them, so they describe different treatments. We can have a growth, and then we can have some management activity. Let's say there's no management, and then there's final felling. And these A matrices describe which proportion of each cell is managed according to these activities. So if you sum up all the A matrices, you get ones in every cell. Matrices of unity, basically. As a first step, you multiply the initial state and then the activity matrices. You get intermediate matrices where you have proportions of different activities. And then when you multiply these matrices with the transition probabilities, you get the next state of forest. There's two matrix multiplications, and this is repeated as many times as you want to simulate. So for example, we have 5-year time steps. We repeat these steps for example, 10 times. We have a 50-year time series simulated this way. When I said in the beginning that this model can be downloaded, it's available as open source, it means that what you can download is so-called EFDM core, and you can download some add-ons. But basically what you get when you download the code is this framework, modeling framework. And then it's up to the user to specify the different input matrices, specify scenario assumptions, how to use the model. But this generic framework you get by downloading. And if you think for which purpose this is useful, it can be used, for example, between European countries, so that the national forest inventory teams download this framework. They are the experts of inventory data, so they parametrize it themselves. But because the modeling framework is standardized, the outputs are probably comparable, at least much more comparable if all countries did this modeling using the crowd models of their own countries. So this is one very interesting application that we have tested this so far. A few words about how to parametrize the EFDM or how we have done it. We have used Finnish National Forest Inventory data for parameterizing the model. We always model the area of about 21 million hectares, so it's really a large area simulation approach that we do. We define management by means of this kind of forest use restrictions. So we have protected areas, we have these forest legislation targets. For those we simulate only natural processes, so there's no management for those, about 10%. Then we have also some other areas that are not completely restricted, but there are some restrictions that do not allow, for example, final felling. There's another 10% for recreation uses and so on. So those are restricted in our simulations, and for the rest of the area we assume that even-aged silviculture is applied. We model the transition probabilities from permanent NFI inventory data, about 12,000 plots. So what's the benefit of this approach? Again, is that we don't actually need a growth model. We are not restricted to some uncertain modeling approach, but we can derive what is realized growth from the permanent inventory plot data. What has happened in those plots for the past 5 years? Of course, I must say that of course we don't have enough observations, so we need some type of modeling. But anyway, the approach is a little bit different than using growth models for this purpose. We also need information about operations. We have combined a stand-level simulator for that purpose with our model. Because we simulate the development of area, we need output coefficients to translate those areas to carbon, and then we need a few more parameters that I get back a bit further in this presentation. But then I would like to go back to the title of the presentation. So it's uncertainties due to climate change and forest management. And if we apply the transition probabilities from the previous inventory, we would basically replicate that time period also in our future simulations. But because we want to take into account the effects of climate change, we have developed an approach how to adapt the transition probabilities to changing climate, to what we estimate that would happen due to climate change. And in this estimation, we first of all try to model what happens to climate parameters that affect tree growth. And these values we basically get from climate researchers. We don't do much in here. How to model the effect to the tree growth? We have used functions developed by Juho Matala and from Seppo Kellomäki's team, so they have published those. They describe it in terms of so-called relative scenario effect, where when we plug in the increased temperature and increased CO2, we get a kind of multiplier for the volume. How much additional growth should the volume have according to this model? And we take this scenario effect as a trend in our model, but we don't only model the trend, but we add this trend with stochastic variation that has been observed in a past growth series. So we assume that there is a trend due to climate, but around that trend there is similar stochastic variation as earlier. And we need to take a few more steps to take this to this matrix modeling system, but basically this is the background how we account for the climate. What you must notice is that we assume that there's only positive effect due to climate change. So we don't take into account disturbances in this approach. We only model possible additional growth. If we knew how disturbances affected in the same way, we could take also those into account. We also could take into account a more detailed look at the uncertainties. What we get by plugging in these different sources of uncertainties in our model, we get projections. Our baseline projection is described by these bars. These uncertainty sources are described on top of the bars. So there is one certain degree due to forest management, which basically comes from different harvest allocation. And then these colored curves, they describe what we estimate is the effect of climate change. And what we can see that if we allocated our harvests in a slightly different way, it means that if we followed or our forest owners followed the instructions of good forest management, we would already get a similar kind of climate impact than if climate warming occurred according to these different RCP scenarios. So there is increased potential in growth in this sense. And again, I say that if we knew the disturbances, we could take same kind of approach to estimate the uncertainties for those disturbances. I have a prepared set where I describe it in more details. You can read it from the publication. This is something that I want to highlight. There's lots of talks about how much total harvest amount affects. There's not much talks about how the allocation of that total amount would affect. And as important as the total amount, or even more important, is the allocation of that amount. So if you allocate even 60 million cubic meters per year badly, if you harvest all the young forests, it's not good for the climate, and it's not good for the production either. These diagrams describe the difference between business as usual, what forest owners do, and what they should have been done according to instructions. And there's really what they can improve in that sense.
Sorry, I cannot stop this.
Don't worry, I like this kind of background music. It's yeah, it's a signal that I should stop probably. I get that. Just some concluding remarks. So we motivated this study because there was a legislative proposal. Nowadays it's legislation on LULUCF regulation, how to include greenhouse gases from the LULUCF sector in the climate and energy framework. a key principle of that legislation is that you should continue past forest management. You should project the continuation of past forest management. And according to our experiences, actually it's not a good approach. So future uncertainties should be accounted, and the forest management should be able to react to these uncertainties, and projecting past is not a good approach. So there is something to do with this LULUCF regulation, certainly. This approach that I have presented would be transparent and feasible to account for these uncertainties. The degree of uncertainty could be estimated as the difference between the baseline scenario and these uncertain measurements. And if we develop this approach a little further, there's a chance to make kind of Monte Carlo type of simulations. But at this point, I conclude, and I thank you for the attention.
Thank you, Jari, and we certainly have time for one or two quick questions.
Thank you, Jari, for a nice presentation. When you do the matrix model, you showed 20-year age classes and 100 cubic meter volume classes. Was that just for illustration purposes?
Just for illustration.
How big are the classes in reality?
I don't remember them by heart, because there is a kind of dynamic division.
Okay. So what happens if you have 5-year time steps, but some stands may not transition from one class to the next within a time step?
Yeah.
So does that class then have no volume increment? And when you get the transition, you get the whole volume increment of the whole period from one class to the next. Is that how it works?
Yes.
That's how they normally work, these matrix models.
That's
right?
basically so, but because the transition probabilities are estimated from vast amount of plots. So there is certain plots that remain in the same class and certain proportion that move to the next class. But they are not like the mean value. There's these initial volume values around the mean. So basically it should reflect from the transition probabilities.
Thank you. Any other quick questions?
Well, when I read your presentation, I was really expecting that the main focus would be on the latest slide that you have put, and I'm quite surprised that if we are discussing how boreal forests can mitigate climate change now, not in the future, with all this research, shouldn't we at least mention what's the position of Finland right now, also concerning with this land use change and forestry legislation, and why is it doing so bad, and why there has been so much controversy, or at least mention it, because this is having a huge impact not only in Finland but in Europe, and it might also impact the whole world if we take as granted that burning forest biomass it's a good thing and that we shouldn't count. So I don't know why.
Yeah, that's
you didn't mention it.
That's a valid comment, and I think I would answer it that it's related very much to this system boundaries what you define. So and you are able to study certain elements of the system only. So this study was about uncertainties in these projections. If you would like to do, or what I understood, how you said the study to that direction would involve different sources of energy, how biomass contributes to them, and how wood can be used in other ways. So I think it's much wider system than what we considered in this simple presentation. But valid point, definitely.
Thank you once again, Jari, and we will move on. I will shortly introduce you IBFRA and IBFRA Insight. process, and then we continue to panel discussion. Maybe the mic, you turn that to Tuula already in this point. So in the very beginning, I already told that IPFRA is International Boreal Forest Research Association, and IPFRA have initiated InSight process, which means that we are aiming to increase and enhance science policy dialogue. And because of that, IPFRA is preparing a scientific summary report on topical issues that are relevant to Boreal region, circumboreal region. And this process is to be supported by scientists who are authors of the report, of course, and Boreal countries and their funding agencies as a source of financial support. And it's already so that first topic for such InSight process is selected is sustainable boreal forest management, which is challenges and opportunities for climate change mitigation, which was topic of the day's discussion so far, and especially in the forthcoming panel discussion. This IPFRA InSight process is, and this first topic is coordinated by SLU, where scientific lead is with Peter Högberg, and principal author is Lisa Andersen Seder, and Future Forest Program Director Annika Nordin. And from IPFRA, who are involved, is task group where Werner and me and Rasmus Oostrup are involved. And this will be the first topic of the IPFRA InSight process, and following ones they will be agreed with IPFRA and Ministerial Circumboreal Working Group. And questions which are addressed by this first summary report are here. I don't repeat them, but I want to say that nomination of the authors, scientists who are involved, it's now under process. In coming days, I will send an suggestion who will be a Finnish author. So if you are interested to be involved, please let me know, and we try to get you involved either as the lead author or contributing author in some phase. And the timeline will be such that there will be a workshop with the authors, and then period for the writing and review process. And the work will be ready by November, December this year, and hopefully submitted also to peer-reviewed journal. So that's all about IPFRA process, IPFRA InSight process in this stage, and now it's turn to go to the panel discussion, and I want to introduce moderator of the panel. It's Tuula Packalen. Tuula have a great career as a scientist and modeler, and she have developed tools and approaches to forest planning in Luke and in previous organizations, but at the moment she is director of the thematic program at Luke called Boreal Green, and it's a great pleasure to have you as the moderator of this panel, and I will give the floor to you. And you have the microphone, but the panelists will use this.
Yeah.
Thank you.
You can give it to me. You can. Yeah, no, but I'll give it to the panelists. Okay. Thank you, Raisa, for the kind words. And I would like to invite the panelists here. So today we have 4 panelists. Our guest star, Werner Kurtz from British Columbia. And then we have our new professor in business economics, so how do you translate it?
Business development and economics.
Okay, Katja Lähtinen from Luke, and forest policy professor from Luke, Jussi Uusivuori, and then Anna Repo, was it so?
Yeah, I am new postdoc in Luke.
Okay, welcome. So because we have limited time, I don't give any introduction. I just give the microphone to the first and our newest person in Luke, and we have asked each of you to prepare roughly a 3-minute introduction from your point of view to the topic of the day. So, Anna, the floor is yours.
Thank you. So the question was that how boreal forests can contribute to climate change mitigation. And I see that there are 2 ways, kind of obvious ways. One is as a carbon sink and storage, and the other one is as a source of materials, biomaterials and bioenergy. But as we know, these 2 ways are partly exclusive, and we need to be aware of this trade-off when we are designing these new policies and practices. How do we use our forests? So I think it kind of boils down how to deal with this trade-off to 3 questions that I'm interested in my research, of course, is that how do we manage our forests? What products do we do? And how do we make these products? So related to buzzwords like circular economy and resource efficiency. I will give the microphone to Nick.
So you can give the microphone to Jussi.
Yeah, thank you. I'm going to extend the scope of the attention to economics and policies, because that's the field that I have been doing research recently with my colleagues here in Luke and elsewhere. And it's because it's very topical subject matter at the moment here in Finland. We know that Finland is facing parliamentary elections in April, and all the political parties, they are more or less pro climate parties, and they also are they have their opinions in terms of how forests should be managed. At least they have been asked about this. But not only in Finland, but there have been some very interesting initiatives elsewhere, actually worldwide, in terms of policies and climate change. In January this year, a group of eminent economists in the USA, they wrote an article in Wall Street Journal. Basically, they were arguing for USA to impose carbon tax policies that would hit all the sectors. It would be based on pricing carbon, starting at a fairly low level, but then increasing gradually. They are most likely they were influenced by example from Canada, namely British Columbia has had a carbon tax since 2008, and there it has worked quite well, and the GDP of British Columbia has grown more than elsewhere in Canada. So carbon tax is one possibility, also related to forests. Then another approach is ETS, emission trading system, and that we know the cases of California, European Union, and now recently also China is piloting with ETS, emission trading policies regionally, but also nationwide. If China will adopt that policy, it will be the largest single emission trading area. So the role of forests in these policies is a subject matter that I would like to be discussing here today.
Okay, thank you, Jussi.
Okay, and my scope, I guess, in this discussion would be the business economics point of view, and I think that when discussing that how boreal forests can contribute to climate change mitigation, is that we can think it also from the perspective of ecosystem services and how we are using different types of ecosystem services in value chains to develop different types of products and services. And one example is using wood, of course, in short-term products, wood-based products, but more importantly in these long-term products, and more specifically in wood construction, and also related to housing and using of buildings also in terms of energy. And one important aspect, I think, is that not only thinking about the current type of building that we are doing, but also developing these systems, because industrial wood building offers many options for flexible design, for example, that after some buildings have been made, no matter whether they are private homes, for example, multi-story buildings or public buildings, wood offers many possibilities for resigning and renovating the buildings in a way that even if there are changes in people's needs, we don't have to rebuild the whole building. So not only in terms of from the perspective of circular economy, we can think the side products and life cycle issues from that perspective, but also thinking that the products as themselves can be modified in houses. And another example is still, I think, that this is the more kind of an indirect impact that is what's going on in the markets. And that I think that if people are more aware of the benefits of wood, for example in housing, we have the opportunities to nudge consumers' behavior also more broadly towards sustainable lifestyles. And if they are familiar, for example, with forest ecosystems, maybe also possibilities for local tourism, nature-based tourism, can be developed in a way that indirectly it offers possibilities also to decrease climate change impacts of traveling, for example. So more broadly.
Okay, then.
Since I already had the floor for a while, I'll try to keep it very short. From my perspective, what is important when we try to deal with climate change mitigation potential for boreal forests is that we apply the best possible science in our analyses, and that we inform policy decisions based on science and not on emotions. And the reason I say that is because there are clearly choices that we can make that are not climate effective at all. And some of the great increases in some bioenergy uses are clearly going to be problematic, while other alternative uses of a limited resource, like you just said with building materials, are far more climate effective. So it's really important that it's not the influence of the lobby group, but the influence of the scientific analysis that informs the policy decisions, so that we don't do counterproductive things because we don't have time to screw up too much.
Okay, thank you. I'll take this microphone because I have a task for all of you. I don't have brown envelopes, and you get it already now almost in the beginning of the panel. You get white envelopes here. So while you open, I'll explain your task. Actually, it was interesting that I got already your responses during your presentation. So you get 2 cards. S stands for synergy, and T stands for trade-off. And my question to you is that if you consider the use of wood and forests in climate change mitigation, wood can be used in several ways. Wood can be used to substitute fossil-based raw materials and energies, and because growing trees store carbon, Forests as such are carbon sinks and storages, but harvested trees, when put into long lifespan wood products, they can store carbon even longer than in trees which they originally come from. So, do you see that the role of wood and the role of growing forests, they are in synergy, or whether they are in trade-off between each other, considering climate change mitigation? And you can select your own point of view. You can define your own system boundary, whether in time and scale, whether you think globally, whether you think one stand or something in between, and what is your lifespan. And Jussi, you can even think from your policy point of view that if you have a kind of future where you would like them to be in balance, what would be your policy means of achieving this? They look pretty.
They look as if they are thinking of each one.
Okay, you can start. I'll give you the microphone.
Well, I took the synergy, but I didn't necessarily think so much. I think that it's anyway a question about a system, in a way, how ecosystems work. And we can think, I try to think from a positive point of view, in a way that it's not a question of either or. In some cases, if we think about forest uses, there are areas and the type of forests where one should keep on growing and keep the carbon in the forests. And then there are options to develop different types of systems. So I think that I'm trying to look from the positive point of view, in a way that there are synergies. Instead of, if we think about trade-offs, we end up in a situation that we basically, I think, cannot do anything. We're stuck in some solutions.
Okay, who wants to continue? Anna. Okay, you can.
I chose the yellow one because it was Cooper on the year 82 or something like that that showed mathematically that if we maximize the sustainable yield, if we maximize the amount of forest that we can take sustainably out, it doesn't maximize the carbon stock. And so therefore I go for the trade-off. And but if we want to go for the synergy, that might be possible, but then we really need to rethink how do we use the wood that is taken from the forest. It requires, as Katja says, long-lived products. And in Finland currently 60% goes to pulp industry, and that's not very long-lived currently. But there are these new kind of avenues of research where they are trying to find new ways to use also pulp in products that have a long life cycle. So this, but we may go for this.
Yeah, I would choose actually the two of them at the same time, trade-off and synergy, because I think there are cases where both apply, or either one apply. And I was talking about maximum sustained yield, and being a forest economist, I know that depends on which side of MSY, the rotation wise, we are kind of operating, then whether we are increasing the forest use or not, then it reflects to whether the annual potential cut is going up or down. So there are cases where either one of these options would apply. So I go for the two of them.
Okay, already 3 different answers. This is great.
And I'm going to sort of skate through the middle and add disturbances to this. So first of all, I agree. It can be synergistic or there can be trade-offs. We need to understand that the goal in order to achieve climate change mitigation is to maximize the amount of carbon dioxide that we remove from the atmosphere. And we can do that by managing forests in such a way that they are strong sinks. And that can be done by harvesting periodically. How we do that is another discussion, whether we use clear-cut systems or continuous cover systems. Again, trade-offs between them. How we use the wood is absolutely critical. I think I tried to make that clear in my presentation. And what we haven't talked about in this discussion here is the interaction with risks from disturbances. And so where I see opportunities through forest management is that we look at the type of risk that is faced in different boreal regions of the world, and that through active management, we do things like manage density of the stand, either for the purpose of avoiding insects or reducing drought, and so on. I think that the last point I want to add is that certainly in Canada, and I think to some extent in Russia, there has historically been a forest management model that was clear cut, regenerate, walk away, come back, 100 years later, clear cut again. I think there are tremendous opportunity for carbon management through thinning, partial cutting, and other activities aimed at extracting some wood out of the forest that would otherwise go to mortality. And I didn't show it in my presentation, but there's a huge difference in the proportion of net primary productivity that is captured for harvest and for growing stock increases in Sweden compared to Canada. And the difference is because we don't do thinning, hardly at all. Whereas in Sweden, that is an active part, and in Finland, an active part of forest management. So there are tremendous opportunities among boreal countries to learn from both the successes and the mistakes that were made in some of the Scandinavian countries. And that's another reason why I think there's strong synergies.
Okay. Thank you. This was really good. I was a couple of weeks ago in Brussels and we were discussing a lot of trade-offs between different forest ecosystem services. And one of the DG representatives said that, why are you talking about trade-offs? You should be looking for synergies. So I think that Anna and Jussi, you hit the nail that we should be really, and what Katja started, that we should be looking for synergies, because there we get the win-win situation. But while you have these voting tickets there, I have another question on these synergies and trade-offs, because it seems to open your Pandora box. Katja already mentioned that we have several ecosystem services. If you categorize ecosystem services, you have these production services, then you have regulating services and maintaining services and cultural services. And climate change regulation of climate is only one of the ecosystem, one of the many ecosystem services. And for example, climate change adaptation belongs to these maintaining services, but we have other production services than wood. We have non-wood forest products, and then we have recreation, which relates to cultural services. So you can now pick some of the ecosystem services you think is very important, that where forests have a big role, and then you can maybe you can find one that is well in synergy with climate change mitigation, and another one where you have the biggest trade-off from your point of view. So think of 2 ecosystem services, one for which you can use your green ticket and one for which you can use the yellow ticket. Somebody may help by listing some ecosystem services if they forget what they are. Nutrient cycle. select one which is very well in synergy with climate change mitigation and one where you have the biggest trade-off. You want to start?
Why not? I mean, I think the ecosystem service of greenhouse gas management is clearly the one that's most aligned with climate change mitigation options. And where I would take the potential trade-off right now is with some biodiversity aspects. And I shouldn't be talking about it because you guys know it better than we do. But one of the consequences of the intensified management that I spoke about a few minutes ago is that the mortality that would have otherwise occurred in your forest has been extracted and is used for various products and services. And so what that means is that you have less dead organic matter in your forest. What would have died and decomposed is instead extracted and the energy is used for human needs. As a consequence, certain species that are dependent on these dead organic matter pools are threatened. And when we talk about intensification of management in North America, people always point to Scandinavia and say, oh, but look at the damage they have done to biodiversity. And where I see the problem is that the intensity of management in Fennoscandian countries is, and you showed it earlier, 90% of the forest was under some form of harvest and management. The fractions in North America are, and certainly in Canada, are much, much smaller. In other words, we could move a long way towards a Scandinavian model of forest management, and we may have site-specific adverse impacts on biodiversity, but not necessarily landscape-specific adverse impacts on biodiversity. And so, again, from a research perspective, I would like to understand better what these trade-offs are, and also what the consequences are of some of these, not necessarily losses in the terms of extinction, but reductions in abundance of some of the elements of biodiversity. And put that reduction in abundance in the context of the impacts that climate change will likely have on these same species.
Okay.
I started to think that something that might be, well, I guess in synergy is one is soil formation. I mean, how the soil is, the condition of it is important. But one thing that occurred to my mind, this is a bit provoking thought, but I think that one is cultural heritage to some extent, that there is some trade-off, because some traditions that we are having in our forests in Finland regarding management, but especially internationally, are not necessarily good at all. So traditions are good to some extent, but sometimes they may have adverse impacts on ecosystem services, other ones, but also regarding the climate change mitigation.
Okay.
Okay, I'm not an expert in biodiversity, but my kind of thinking goes along the lines that climate benefits of forests are in synergy with the biodiversity services. In the modeling work that we have been doing, when we correct what is called policy failures, I explain what it means. It means that currently the markets are not pricing the climate services of forests, not at least correctly. So when those are corrected in the modeling, it leads to older forests being grown. Forests are grown older, and just I think that means that there's more biodiversity in older forests than in younger forests. So trade-off situation might be what I could conceive of scenic values of certain policies if we choose, like in Finland, we have been talking about deforestation programs, so that perhaps agricultural farm land would be afforested. So perhaps we are losing some scenic values when more and more landscape is becoming so-called closed. But that, of course, depends on our preferences. But that's a possible trade-off.
Can I have just a comment? And actually, I would like to give the microphone to Werner again. Did I understood right that you don't agree on the relationship between biodiversity and climate change mitigation? So I think you may have some differences in your system boundaries or system development, and I think it would be important for us to understand your different point of views. Werner, can you pick up what was the difference?
Yeah, I was struck by that too, because what you said was that if you price the climate service of forests, that will result in older forests. And that is based on a system boundary that excludes harvested wood products and substitution benefits, because otherwise you couldn't necessarily come to that same conclusion. So I mean, is that how you drew your system boundary? Because, well, and I guess the question is how much older, right? What I heard you say was that because you price the carbon, you will change your management such that you have more older forests, and therefore you will get better biodiversity, right? Okay. And so did that system boundary include harvested wood products and substitution benefits?
Yeah.
Okay.
Yeah, the system boundaries are such that there's the wood products are included, so that if you price the carbon content also of the wood products as well as carbon in forests. So initially, at least, there's a fairly strong move to older forests. So perhaps then in the long run, there will also be more wood cut from bigger forests, but that happens only in long run.
Okay. Are you happy with the answers? Do you want some clarifications? Okay,
I
you want
continue
to.
with the same topic because I think my thinking is kind of in line with Werner's thinking. That, or maybe I give an example of a study that we did. We were interested in large scale. If we go for large scale bioenergy production from forest harvest residues, so stumps, branches, other residual biomass. So what's the effect on carbon balance? So this kind of trade-off between carbon balance and bioenergy, and biodiversity. And in that study, we saw that there is a negative effect on deadwood-dependent species, but we get some climate benefits because of emission savings. But these emission savings come with a delay, and this kind of delay in the emission savings is the problematic thing from the point of view of climate change mitigation.
It's a problem, or it's the key of the problem that delays 50 years. We are talking we have to do something in 10 years.
Okay. Do you want to add something?
It depends, once again, because this whole debate around bioenergy often fails to recognize the importance of where the wood is coming from relative to the business as usual scenario. And I give you the most egregious of examples, and that is in British Columbia, as a fire risk reduction strategy, we still burn harvest residues on site after harvesting. And we release about 5 million tons of CO2 into the atmosphere as a consequence of that. Simply changing that policy, and instead of burning that wood on site, removing it from the site and turning it into bioenergy will give you a climate change benefit that is almost immediate. because the fate of that material would have been instant, well, relatively instant oxidation as a result of burning. And there are numerous other examples. So we really need to differentiate our discussion of mitigation options and mitigation policies with an understanding of where does the wood come from? What is it that we're substituting? You know, what's the rate of regrowth, et cetera, et cetera. And there's some really nice studies that were done in Canada that basically show different policies of bioenergy use and under which conditions they will always be a winner, you know, after 10 years in the best case scenario and 50 years under worst case scenario. And there's some that will not be a winner in 100 years. And so it really depends on what it is we're using the wood for, what would have been its alternative, et cetera. And so we must be very, very careful with two things. Simplifying policy assumptions like bioenergy is always carbon neutral. Don't go there, right? It's just we need to understand what the impact is on the atmosphere and when that impact occurs and when the benefit occurs. And as you saw in one of my examples, the bioenergy curve caused greater emissions. It wasn't coming down until decades later. And people need to understand that. The future sink that occurs as a result of the regrowth of a boreal forest is not equivalent to the emission that occurs today. We can't offset. We need to understand the time dynamics of these things. But it's not always as bad as this 50-year cycle, depending on where the wood comes from in the first place. And this is why it's so important that we elevate the quality of the dialogue that we have about these issues. This black and white Twitter feed, bioenergy is bad, bioenergy is good, it's carbon neutral, it's not carbon neutral. Leave that to the social media. As scientists, we need to really understand when we say it depends, that we can go to the next step and explain to the policymaker, and here's what you need to understand. This is what it depends on. And therefore, this set of choices may be beneficial to the climate, and those sets of choices are not. And if we can't provide that sort of dialogue and distinguish a good from a bad choice, we're not doing our job as scientists.
That was useful, I think, for all of us. Yeah.
We are supposed to be interacting.
Yes, sure. If you have something important, do you want to have?
You say it depends on the conditions. It depends on the conditions, but we know what are the conditions in Finland. And in Finland, they are planning to double the forest biomass for bioenergy, and it's aiming to substitute coal. And they say really proudly that they are going to ban coal, but if that's going to replace, like if that's going to just change that they just burn more forest, that doesn't change anything. And it's just contributing even more. And I don't know how can you not be talking about that, because Finland is not only not going for the change, but it's going on the contrary of the change. And that's also affecting to the European Union.
Okay. Maybe I'll yeah. So, do you want to say something? Yeah.
I have a short comment on that. In general, in the discussion that we are having regarding bioenergies, that we are burning forests, I mean biomaterial as such. In Finland, we are burning side products. And that's the important thing to understand the system, that basically when it comes to timber that can be used for other sources, we are not burning good quality timber. Yeah, but so stumps, well, less nowadays. Stumps are problematic, like there has been a research made in Syke, well, quite many years ago, for example. Yes, stumps, but I mean when simplifying things, like burning forests, conceptually, that's not the case.
Yes, let me comment on this. That they are burning wood is not carbon neutral, and the assumption in the European emission trading system now is that that wood is carbon neutral and emission free. That's the policy now, but that's wrong. It's not. Now Europe is planning to impose what is called a reference system for forests. And that can be seen as an effort to actually remedy some of the problems that takes place in the ETS emission trading system of allowing wood use to be emission free, so that they are imposing certain requirements in terms of the forest sinks. But as we have been analyzing the reference system of forests, it's quite cumbersome, it's convoluted, and it does not have the proper incentives. So from the point of view of the economic analysis is that what we need to identify are the policy and the market failures in terms of the carbon and climate benefits offered by forest sector, not only forests but also the use of forests. And then identify all the emissions and sinks, and then design the policies accordingly, using taxes and subsidies in proper places, and then you price the climate benefits and the damages appropriately, and then you let the markets work their way. That's the simple recipe offered by economics, and the philosophy is quite different from the dispute that's going on currently in Europe and in United States, North America, is that how can we maximize the carbon balance of using forests.
I just want to add to this statement about carbon neutrality. Carbon neutrality is a policy construct. It's not the impact on the atmosphere. And part of the reason why the energy sector can claim that burning wood is carbon neutral is because the land sector reports the emissions from the burning of wood in its greenhouse gas inventories. So when we ship pellets from North America to Europe so that they can be burned, the European energy sector claims that they're carbon neutral. They're not reporting the emissions because those who ship the pellets have to report these emissions in our greenhouse gas inventories, land sector. So it's not carbon neutral. They are, as long as the shipping and receiving, or the harvesting and the using entity, this could be within a country or across country boundaries, as long as those who harvest the wood report the emissions associated with the wood use, they are showing up in the greenhouse gas inventories. They're just not showing up in the energy sector. And the consequence of that is that we make the wrong policy decisions because we think that the benefit of using woody biomass for the atmosphere from the energy sector's perspective, is far greater than it actually is as far as the atmosphere is concerned. In fact, it can be, as you said, negative, or not having a benefit for 50 years until the regrowth of the forest has occurred. So carbon neutrality is a policy construct that can lead to really bad decisions. And what we need to do as scientists is demonstrate alternative wood uses, as you said, with long-lived wood products in buildings, etc. And so then we can show people, hey, why would we use wood, which is a finite resource, to produce something like electricity that we can now produce far cheaper using photovoltaics and other non-carbon emitting solutions, and then we can use the wood to put us on deep decarbonization pathways, either for building, and then we can use the residues to do things that we can't do with electricity, like long-range transport or flying airplanes, etc. So I think we really need to understand what our options are and how they relate to climate change mitigation. And policy constructs like carbon neutrality don't help in that process at all because they distort the outcome.
Thank you very much. This has been really exciting to listen to you, and while we are running out of time, I would like to make some conclusions, especially for Raisa. what I got from your responses is that we really need to define our systems, system boundaries, whenever we are discussing between researchers, and especially when we are talking to policymakers. And researchers need to position their modeling results into the whole framework, that we cannot always just present the model results directly because they don't tell the whole truth. That's what I got from Kurt's response. And I think for Raisa, who is coordinating this IBFRA work, it's very important and interesting to learn that in different conditions and in different countries, the challenges seem to be a little bit different. And if you need to cover the whole Boreal zone, that's really crucial for you. As a final comment, I think that in Finland we have very good technology companies who prepare these wood energy mills. So maybe we can give you as a gift names for those companies, so that you may consider to take it as a home-taking message, that instead of burning residues in the forest, you could use it for some other purpose. But thank you very much. It has been a pleasure to be here, and thank you all.